Yep. All right, here we go. Let's talk about the intermediate value theorem. All right, so formally, the intermediate value theorem is going to read as this. If a function f is continuous on a closed interval a, b, so in other words, I can trace it without lifting up my pen, like this example I have right here. This can be traced without lifting up my pen. And there's some c, which is an element of the set of reals, just basically means that c is a real number, such that this number is between f of a and f of b, as depicted in this picture. Then, right, do we know what this cool symbol is? Right, hopefully you do. That means there exists, and then there exists an x in the interval AB, such that f of that value, f of x, equals c. So it's a little weird when you see it formally, but informally, it makes a lot of sense. It basically says, listen, if you go ahead and you trace a function and it's continuous, so you can trace it without lifting up your pen, and you look at what the y value is at one endpoint right here, right? Say we got f of a. And then you go look at what the y value is at the other endpoint, f of b. Well, then you're guaranteed that every single value between f of a and f of b must have occurred at least once on this graph. And that must make sense to you, because if I'm tracing this without lifting up my pen to go from one endpoint to the other endpoint, I'm going to have to pass all these values. So it's the values that are in between the two y values at the endpoints that are guaranteed. All right, so that's what we got going on. So it's not really too earth shattering, to be quite honest. All right, but it's a cool little theorem nonetheless. All right, so let's look at a question. Let's see how this plays out. All right, so it says, all right, let's let y of t equal t squared plus 1. Is there a value t on the interval 0 to 4? Now, I made it open. Maybe I should have closed it. It's kind of not going to matter. So is there a value for t on the interval 0 to 4 such that y of t is equal to 14? So in other words, does the functional output, is it ever 14 on this particular interval? And then justify your answer. So you're like, all right, in order to do this, it's pretty simple. You're going to look at the endpoint at the functional value at one endpoint, which is 0. And I know we don't equal 0, but we're going to pretend for a second like it's or equal to, and see what we get. We would get the output is 1. All right. Then we would look at the functional value at the other endpoint and see what we get. We get 4 squared plus 1, that's 16 plus 1, that's 17. So now, because y is continuous, which, by the way, is y continuous? Yeah, you should know that, because it's a what? It's a polynomial, right? So we can say something that y is a polynomial, therefore y is continuous, really everywhere. So if I know the function's continuous, and I know at one endpoint I'm at a value of 1, and at the other endpoint I'm at a value at 17, well, then what's between 1 and 17, right? This intermediate value, 14. So we can say by the intermediate value theorem, right, there's going to exist some x on this open interval, 0 to 4, such that, right, y of x equals 14. I should have said t, but it really doesn't matter. All right, so hopefully that makes sense. And let's go ahead and look at the graph, and maybe it'll make more sense, right? So here we go. So here's just a parabola. Y equals, x squared plus 1, same thing as t squared plus 1, just instead of an x-axis, it's a t-axis. And now notice what I did. I know the interval is open, but I looked at the functional values at the endpoints of my interval 0 to 4. So even if we made these open, we're still getting close to those values because the function is continuous there, right? So now you're trying to figure out, can the function take on the value 14 anywhere in this interval? Well, yeah, it certainly can, right? It hits 14 right here. In fact, it's going to hit every single intermediate value between 1 and 17. And that's what the intermediate value theorem is. And again, I can only do this tracing thing and say that I'm guaranteed to hit every single value for one big reason. And that reason was really the hypothesis of the theorem. And the hypothesis is the if part in the theorem. That's if the function is continuous. So as long as it's continuous, I'm guaranteed to have all of these intermediate values, right? Not the most exciting thing in the world, but still cool nonetheless. All right, now let's look at the next one, because this maybe I would argue is slightly more exciting. So there's an important existence application here. when your endpoint values are opposite signs. So think about that. Say you go ahead and test the functional value, you figure out the functional value at the right endpoint and you get positive, and then you do the functional value at the left endpoint and you get negative, right? Well, what's a really important value between positive and negative? And hopefully you're saying 0. So then that would let you know that the function has to take on 0 at least once in that interval a to b. And if this function is f of x, then that's basically telling you there's at least one solution to f of x equals 0. So it's like, doesn't tell you what the solution is, but it tells you that there's got to be at least one. It tells you that it exists. That's why I said existence application, right? And again, at least one. In reality, right, the graph, if you're only doing this endpoint and this endpoint, and the graph's continuous, in reality, the graph could look like that, right? And there could be a bunch of spots where it's 0. The theorem just guarantees one. There's got to be at least one. So let's use that application. So it says, show that there's at least one solution to this equation. You're like, what are you talking about now? Equation? You're just giving me functions before, and now you're throwing equations at me. Well, in order to apply this kind of concept here, you have to put this equation in the form function equals 0. In other words, get one side equal to 0. So to do that, I can say, all right, let me just subtract 1 from both sides. And now I can say, all right, now it's in the form function equals 0. So my function is f of x, right? Or in this case, x cubed minus x minus 1. Now, what type of function is, and I'll write it explicitly, what type of function is x cubed minus x minus 1? Well, it's a polynomial, right? So I would write, hey, f is a polynomial, hence f is continuous everywhere, right? Or in this case, continuous on 1, 2. So now the intermediate value theorem says, all right, go ahead and test out what the functional value is at one endpoint, right? F of a, that's f of 1, and then test out what it is at the other endpoint, right? F of 2. Well, f of 1, 1 squared is 1 minus 1, that's 0 minus 1, I get negative 1. F of 2, 2 cubed is 8, right? Minus 2 is 6, minus 1 is 5, I get 5. So you're like, all right, what happens here? Well, the intermediate value theorem, right, guarantees that you're going to hit every single y value between negative 1 and 5 at least once. Well, what's in between negative 1 and 5 that we care about? 0, right? So by the intermediate value theorem, there's got to exist an x on this interval, right? 1, 2, at least one x, such that, and really I could have opened the interval up, such that f of x equals 0. So there's got to be at least one spot, all right? Again, let's take a look at the graph here. If I graph fx equals x cubed minus 1, remember I'm looking at it on the interval 1 to 2 here, all right? So I actually got to change this, 1 to 2. So if I figure that out, here's the output when I plug 1 in. Here's the output when I plug 2 in, right? So that's a positive value, that's a negative value. Well, there's at least one spot, and you can actually see there's at least one spot on the interval 1, 2, right, such that the function is equal to 0. So that basically tells me that there's at least one solution or one real solution to this equation. Again, it didn't tell me what it is. It didn't tell me it's 1.325. That I wasn't able to do. I was just able to know that it existed and specifically existed somewhere between 1 and 2. And in math world, sometimes it's really important to know that things exist, even though initially you might not know how to find them. All right, there's your intermediate value theorem. All right, that is it for the weekend. You got a lot to do. Watch all those videos, take all those notes, and submit them on AP Classroom. Be good.